third topic of our conference is joined with dynamical systems center of INPA. And it's my pleasure to introduce John Aaronson, who will talk about inner functions.
Revisited. So thanks for inviting me. Very nice to be here. And I want to say happy birthday to both of the birthday boys, even though, as you can see, it's part of the Institute. It's also nice to be back after the COVID and maybe let's hope that it's not just before the World War and everything. So this is joint work with Mahendra Nadkarni. The reason we call it Revisited is that our previous paper on this, both of us had papers on this in 1981. And actually, we should really be dedicating this to a guy called Omar Khayyam. You know him, right? Wine taster, mathematician, various other things. But the point is that he has a poem that he said that he went into mathematics and then he managed to leave by the same door that he came in. And this is what we're trying. But you see that you may see that we still have problems. So it's not so easy. Okay, so here's the menu. So I want to do something called composition operators on the disk. Then, as an example of this, there'll be inner functions. So inner functions, restrictions to the unit circle as non-singular transformations. And I kind of give a review of the old stuff on the ergodic theory. Then there's some stuff on, the question that we were both interested in was to look at the structure of inner function restrictions, which can be quite complicated. And this led us to do something on the structure of non-singular transformations of the unit interval. In fact, we're going to show that they're locally invertible if and only if they're forward non-singular. Okay, which we're calling a folklore theorem, because we don't know. Maybe Rochlin knew this, maybe not. So then there'll be structure of inner functions. So this is structure of non-singular, and specifically structure of inner functions. There's singularities, there are angular derivatives invented by Karateodori, and local invertibility. In other words, when you're sort of countable to one. And then we'll talk about analytical conditional expectations. And then I sort of go to the kind of, I wouldn't say main point, but the main dynamical point is to look at the transfer operators, quasi-compactness of the transfer operators of probability-preserving inner functions on suitable spaces of real analytic functions. So these are kind of interesting because the inner functions are not smooth, but the transfer operators are excessively smooth, and this leads to some interesting, properties. Then we want to do various kinds of central limit theorems for the stochastic processes by various methods. And I'm going to finish off with some possibly stupid questions about the multidimensional case. There will not be any quantum, only multidimensional. So in other words, I look at the bi-disk. I want to look at inner functions on the bi-disk. Okay, so composition operators. I want to take this one slowly because right at the end, I'll be talking about the same title, but the bi-disk. So that's the disk across the disk. So you have an analytic function, analytic endomorphism of the unit disk. You define the composition operator, so you define unbounded measurable functions. So you look at the harmonization, you take a bounded function on the circle, look at the harmonization, Poisson integral, which is a bounded harmonic function. There's the Poisson kernel. And you compose with this bounded analytic function, and then you take radial limits, which exist almost surely. So that defines an operator on when you get another bounded measurable function. So if you had bounded measurable function, which was 0 almost surely, then harmonization would be equal to 0. And so the composition operator would be 0. So in fact, C phi is non-singular. So it's sort of rather trivial. So trivial that actually will generalize to higher dimensions. So that will, if we're still time, we come back to the last slide, and there'll be a generalization there. Okay, an inner function is an analytic function, so that the radial limits exist, well, they always exist, but the radial limits are part of the circle. So you get a transformation from the circle onto the circle, and the restriction of the inner function, well, it's a measurable map of the circle, and the composition operator is actually composition with the inner function. We know that the composition operator was non-singular, so is the inner function. It's a non-singular transformation. By the way, I should say this is supposed to be a long talk, and in order so that it just shouldn't seem long, you should stop me whenever you want. In fact, you'll be doing me a favor, because then I can waste some time and everything. So if there's anything you don't understand, just say something. Okay. So next thing we say, okay, so this generalizes to higher dimensions. Push forward operator. So, I don't know what you do. I mean, I get a bit dyslexic with this kind of thing. The idea is that you pull back the sets and push forward the measure, or you push forward the sets, push forward the function and pull back the measure. I mean, it's I just opted for push forward. So I got the composition operator, and I defined the star operator on measures by integral with respect to the star operator is the operator on the function, integral with respect to the measure. So that's the push forward measure. So I'm claiming this preserves absolutely continuous measures. And so this will follow by, if I take some set with the Lebesgue measure of A equals 0, this implies that the harmonization is 0. Well, in fact, we know it's a non-singular operator. The composition operator is equal to 0 almost surely. And so C phi star mu of A is equal to the integral of C phi 1A d mu, which is integral of something which is 0 almost surely, but mu is absolutely continuous, so this is 0. So we're preserving absolutely continuous measures. Now, for phi analytic, so phi is supposed to be, there's a word analytic which is missing there, and F in L2, or L harmonic or L1, if I define the harmonization of F circle phi, then this is the same as the harmonization of F at phi of z. So this is because harmonic function composed with an analytic function composed with a harmonic function is harmonic. So you get that C star phi of z, pi z is pi phi of z, where pi z is the Poisson measure, because of this thing. So I evaluate integral of f c phi star pi z. This is c phi f d pi z. That m should not be there. This is f phi z, harmonization. This is f harmonization phi of z, which is just the integral with respect to the Poisson measure of phi z. Okay, so why did I go through this? This does not generalize to higher dimensions. So your problem is that I have to get the right concepts of harmonic functions and analytic functions. There are not enough harmonic functions going around, but we'll see that if there's time at the end. Okay. Transfer operators. So I have a non-singular transformation. So I'm looking at the dual restricted to L1. The dual restricts to L1, so this kind of T hat of F integrated against G is F integrated against GT. So for some absolutely continuous measure, I'm going to have an absolutely continuous invariant measure if and only if the transfer operator of the density is invariant. It's a fixed point. The density is a fixed point for the transfer operator.
John, do you assume that T is invertible here?
Sorry?
T is invertible here?
No, not necessarily. Otherwise, I mean, I would be going with T minus 1 times the radon negative derivative. Yeah. So for T inner, I look at the restriction, the transfer operator restriction, and this is the radon negative derivative of the push-forward operator of the measure define the indefinite integral. So by the previous slide, you have t hat pz is p phi of z. So this is appears in a paper of Boole from 1857 for rational functions. I mean, he only had a Cauchy's definition of the integral at the time. Complete proof was given by Nordgren in 1968, calculating Fourier coefficients, and there are various other names by which this guy, I think it's also known in complex dynamics or complex analysis as Loevner's lemma, but I never managed to find any reference to that. Anyway, what you can see is that one way to get an invariant probability is if you have a fixed point for the inner function. So, the idea is that this is the only way. There is this Donjois-Wolff theorem in 1926. What happens when you don't have a fixed point inside? Well, there's actually a point on the closed disk, so it could be on the boundary, so that this will be true. So you get from this that either phi is elliptic Möbius, meaning conjugate to a rotation around 0, or phi to the n tends to this Donjois-Wolff point for every z inside the disk. So in particular, that would mean that if I look at Poisson kernel associated to z and I iterate this, then it goes to 0 as long as I stay away from the Donjois-Wolff point on the boundary. Yeah? And so that means that there will be no absolutely continuous invariant probability if the Donjois-Wolff point is on the boundary. So you see that this is the only way that there's an invariant probability. Okay, exactness. So exactness means that the tail field is trivial, and there's a transfer operator condition by Michael Lin from 1971, which means that the L1 norms of t hat to the n of u tends to 0 in L1 for every u with integral 0. So example, I could take pz minus p omega, and that would have to tend to 0. And in fact, that's the closed linear span of these guys is all of L1 0, so in fact this is general, so t is exact if and only if this happens for every z and omega in the disk. And then you calculate, in fact what's going on is that the geometry, the L1 geometry of Poisson kernels is the same as the hyperbolic geometry on the disk. So this is a formula exercise. And this is the, what is it, arc hyperbolic tangent of the hyperbolic distance or something like that. So that's your condition for exactness. And in fact, you can see that if p is not Möbius and you have the Donjois-Wolff point inside, then you have that the derivative is less than 1, and you have that this goes to Donjois-Wolff point for every z, and you have this guy, which means exactness. Okay, so a little bit of ergodic theory. Pomerenke in 1978 had a dichotomy for inner functions. So either you have this kind of thing that everything gets squeezed together, hyperbolic distance tends to 0 for any 2 points, or there's some bounded analytic non-constant function, so that f phi is equal to f, an invariant function. So therefore you know that. So in fact, I mean, this is my last paper on inner functions before today. If I have something which is ergodic, then it's if and only if it's exact. Before that, there was this result that you can check that t is conservative in Sasha's definition, if and only if you have this kind of Lebesgue condition, because you'd have the sum of the iterates and the t hat, tau hat of the Poisson measures. That would have to be infinite, almost surely, for conservativity. That's a Hopf condition, and that's if and only if you have this guy. So me and Neuwirth in 1978, we used the Lebesgue condition to prove that conservative implies ergodic. So you get that actually conservative implies exact, same as ergodic, and there are examples that you can write down things which are exact but not conservative. So that's the basic ergodic theory in the large. There's some very nice results of Kraser, his thesis in 1991-2. So if phi is not Möbius and the Dangeau-Wolff point is inside the disk, then firstly, the natural extension is Bernoulli, isomorphic to a Bernoulli shift. And so finite entropy is if and only if Rochlin's formula holds. So there's a Jacobian, and you look at the log of Jacobian, and the integral of the log of the Jacobian is finite. And that is actually the same condition that the derivative should be in the van Linne class. So there are two papers there from 1991-2. Didn't see any easy proofs that were written up since then. So one of the things I'm looking at is I'm trying to understand these papers.
And also, is M the Lebesgue measure?
Sorry? Yeah, M is Lebesgue all the time. M is Lebesgue.
So then, what does it mean to have conservativity? Because if it's a probability measure, then won't it?
Yeah, but it's kind of a non-singular transformation, isn't it? It's not.
Sorry. Yeah.
It's a non-invertible, non-singular transformation. Okay, so now this is a couple of things that I want to prove. This is the first one. So, structure of non-singular endomorphism. So, suppose you have a non-singular transformation of a Polish non-atomic probability space, a standard space. So, the transfer operator wants to be the integral over some preimage measure. So, in fact, there is a transition kernel. It's a measurable function that goes from some subset of measured full measure to the space of measures on t-1 x, or nu of x is a measure on t-1 of set x, as in a member of the what do you call it, the dual space, the positive dual space of the bounded continuous functions on x, so that the transfer operator x is actually the integral of f d nu x for bounded Borel functions. Okay? This exists. There's something called a disintegration theorem, which gives you this kind of thing. So here's a folklore proposition. So following are going to be equivalent for the non-singular transformation. First thing is local invertibility. So there is a discrete partition. So that if I look at the guy on every partition element, it takes A to T of A, should be invertible non-singular for every A. That's the first thing.
Just discrete means countable many atoms.
Yeah, discrete. Countable. So invertible non-singular. Second one is forward non-singular. So there is a subset of full measure. So if I have a subset of this subset, and it has measure 0, then its forward image also has measure 0. And the third thing is that nu x should be purely atomic for almost every x in x. So these are the things. And these are all equivalent. So what's standard? I mean, I think it's pretty standard to show that 1 is equivalent to 3, and 1 implies 2. These are standard, so we want to do... So for example, an example of something like this, why we call it folklore, there is a proof in a paper of Rochlin in 1968 that any probability-preserving transformation with finite entropy is locally invertible. So it's an endomorphism, has finite entropy, and then you get that it's locally invertible. Okay, so I'm going to prove that 2 implies 3. So 2 is forward non-singularity, and this should imply that nu x is purely atomic. That's the idea. So we're going to show that if 3 fails, so 3 was pure atomicity, then forward non-singularity fails. So you let W equal to all those points in the space that the preimage measure under their image is equal to 0. Okay? So then I claim this is a measurable set mod n. So this is actually, you can say that this is almost surely the limit, equal to the limit of a sequence of measurable functions. So for every y not in W, then you have that nu ty of y is bigger than 0. So if W has measure 0, then 3 holds. So 3 is purely atomic. Almost every preimage measure is purely atomic. So now you suppose that 3 fails, then measure of W is bigger than 0. So this is a positive measure, Borel set. TW is analytic, universally measurable, and we're claiming that TW is bigger than 0. Well, that's kind of easy, because T minus 1 TW contains W, so that has positive measure by assumption. And a non-singularity of T implies that TW also has positive measure. So TW has positive measure. So now if I look at, so now I'm going to condition on these, what do you call it, this disintegration into transition kernel measures or preimage measures. So if I take a subset of BW, the measure of V is the measure of T minus 1 TW intersect W, and this is the integral over W of the preimage measures of V. Okay. So by Yankov's theorem, and losing theorem, so I'm saying that there is some compact subset of TW, positive measure, and a continuous function from A into B, which is the image of the compact set, so B is also compact. Be continuous, this is contained in W, so that T intersect pi is the identity. So Yankov's theorem is the analytic section theorem. I'm going to have a Borel map onto some analytic set, and then there are inverses, analytically measurable inverses. Analytic measurable inverse is universally measurable. So by Lusin's theorem, they're continuous on a big compact set. So that's what we do. So B intersect T minus 1x, so that's this B, is empty if x is not in A, and it's equal to pi of x, the singleton if x is in A. So that means that nu x of B is 1A nu x pi x, which is equal to 0 because pi x was in W. Pi x was in W, which is, and x is T of pi of x, okay? So you get that B has measure 0, but T of B is equal to A, so the measure of TB has positive measure, and you messed up forward non-singularity. Okay. We okay on that? Move on. Okay, so now I'm going to go to the structure of inner functions. This was kind of general stuff. This was giving, well, what do you call it? You'll see that this is giving less complex proof of something on the structure of inner functions. So we have the factorization theorem. I think this goes back to a guy called Smirnov in 1929. So you have a Blaschke product. Any inner function is a Blaschke product, which looks like that, times a singular inner function, so a non-zero inner function. So here's a description of a Blaschke product. I have to have a zero set, I have to have a multiplicity function, and I have to have the multiplicity the zero function with the multiplicity function satisfies this Blaschke condition. So phi is rational if and only if you're a finite Blaschke product. S has no zeros, so it's also known as a singular inner function. So the regular set is where you can extend over the boundary. So I can extend it over the circle. That's the regular set, and the singular set is where you can't. So the singular set is going to be the union of the accumulation points of the zeros of the inner function, union the support of the representing measure of the singular inner function. Okay? So the restriction will be differentiable at each point, or each point on the circle which is in the regular set. And the derivative looks like this. So you can see that if I have an inner function where the regular set is almost everything, then it's differentiable almost surely, and it's going to kind of look like an interval map. And this is in fact the result of Matt Martin in 1988, that if the singular set has measure 0, then T phi is a piecewise increasing interval. So there is something kind of strange about these singularities. I mean, singularities actually are essential singularities, and they're characterized as a dichotomy of Seidel. We'll be using another couple of theorems here as well, from 34. If I take any interval on the circle, open interval on the circle, this is contained in the regular set, if and only if tau is continuous on I. So tau will always be bounded, but may not be continuous. Okay. So, what do you do when you don't have derivatives? So you have Caratini-Rodori says take angular derivatives. So you say that the function has an angular derivative at xi on the boundary, or it should be on the radial limit set. So lambda phi is the radial limit set. If phi z minus phi xi divided by z minus xi tends from the inside, z goes to xi from the inside in an angular domain to some complex number which you call the angular derivative. So there is the definition of angular convergence. Should be for any, these domains are sometimes called Stotz domains. Equivalently, you could have that the derivative converges to some limit angularly, or for some or for every w in T, xi of w not equal to xi, you have that this integral is finite. So this would kind of be, I mean, if this kind of want to be the, if you look at this as a function of xi, this would want to be this would be a kind of integral which dominates the convergence of the differential, the derivative of phi, the regular derivative. Okay, so here are some results for phi inner. So the first one is this train result. It's one way is Heinz in 1977, Alexandrov in 1987. So the inner function or the restriction is locally invertible if and only if you have angular derivatives almost surely. So other possibilities, Zaxman wrote a very nice review on inner functions, if you want. I recommend that. So he's looking at other possibilities here. So local invertibility is when the preimage measures are atomic, but of course you could have non-atomic preimage measures, and there are examples of inner functions like that. So he says that if I have these kind of integrals, and they're infinite for every lambda on the boundary, so for say I take nu 0, the preimage measure of 0, and these guys have infinite integral for every lambda on the boundary, then each preimage measure for non-zero x is purely non-atomic. So in other words, you have uncountable preimage set for every point. The example for this actually was given in 1965 by William Donahue. So you define mu in this kind of way, so it should be 1 over n squared point mass at log n, and then you get that the integral is infinite for every lambda in the boundary. And so if you define phi so that nu 0, the preimage measure of 0 is mu, then phi is inner with phi 0 equals 0, and so you get very nasty uncountable preimages for every x. Okay, so here's what we're doing in this kind of thing. So first of all, for phi inner, consider local invertibility versus singularity set. That's what we want to look at. So the first result is, well, if I have an interval map, then, if it's certainly locally invertible. First result is topological result. Suppose the inner function has an angular derivative at a residual set of points, so nearly every point, then the singularity set is nowhere dense. We would like to say measure zero, but that doesn't work. Just nowhere dense. On the other hand, a measure theoretic situation is funny. If I take any closed set, then there's an inner function, so I could take the whole circle. Then there's an inner function with locally invertible restriction, so that preserves the big measure, and the singularity set is actually equal to this set E. So one thing we don't know how to do, we couldn't do phi with positive measure E, which was derivative, which would finite entropy. Couldn't do that. So it could be that if the derivative is Nivand in a class, then you have to be an interval. I don't know. Okay, so let's prove these things. I mean, it's kind of quick. I'm doing the proof of the topological result because it's the only time this uses Bayes' simple limit theorem, and it's the only time I managed to use Bayes' simple limit theorem to prove anything. So you define fr of x with the integral of rc minus ct squared, and for r less than 1, this is finite. It's continuous, and you know that fr of x tends to f1 of x, which you don't know what that is. It could be anywhere between 0 and plus infinity. This is by dominated convergence or Fatou's lemma or whatever in both cases. Bayes' simple limit theorem says that if I look at f1 as a continuous function on the Pauli space 0, infinity, including infinity, then the set of continuity points is residual. We're assuming that f1 is finite on a residual set, so C is the intersection of those two sets, that's also residual. So now you say, okay, for x in C, there's a little bounded open interval bounded away from 0 and infinity. So this is ax, bx, and there's an open interval around x. So f1 is stuck between ax and bx on this interval jx. Thus you have that tau is continuous. So by Seidel's theorem, there's no intersection with a singular set, so R phi, the regular set, is open and dense, and S phi, singularity set, is nowhere dense. Okay, so I was just wanted to use that. That's it. So here's the other one. So let's do a construction with singularity set everything. So gamma is countable so that the what do we call it? The accumulation points is the whole circle, so you could take the rationals. Fix some function so that some function on gamma so that epsilon gamma has finite sum. And now you fix a probability on gamma so that pi gamma divided by epsilon gamma squared is finite. So you can do that. So I'm claiming that this integral is finite. Pi is the same measure there, but now on a circle. And I'm claiming that this is finite almost surely. Why? Because for almost every point in the circle, and in almost every point in the circle is not going to be in gamma. So let's say we're outside gamma. There's a finite set of gammas, so that if I'm outside this set, x minus gamma is bigger than or equal to epsilon gamma. So this has finite sum. The set where this is less, the measures have finite sum. By Borel-Cantelli, this is true. So therefore you get that this integral is the sum over the gamma 0 and the rest of this guy. And this is some finite number. The first guy is some finite number, and the next guy is less than or equal to pi gamma over epsilon gamma squared, which we fix to be finite. So now you define function from the disk into the right half plane by this kind of integral with respect to pi, and then you define phi by f minus 1 over f plus 1. And f0 is equal to 1, so pi 0 equals 0. Pi is singular, so in fact we're getting its inner. And pi is the preimage measure at 0, so phi has an angular derivative at ct for almost every t, and so t phi is locally invertible. So that's your example. Okay. So you can see that the singularity set is going to be the collection of accumulation points of gamma. Yeah? So it's everything. Okay, so here's something, this is not so important. So you talk about an analytic sigma algebra. If I take the conditional expectation preserves analyticity. So I look at H2, which is the closed linear span of the positive powers of the exponentials. That's H2 0, all the guys which are in H2 but have integral 0. Alexandrov proved that if C is analytic, then, well, you can show that this defines an analytic sigma algebra. And if it's, this is the only, essentially the only way to define an analytic sigma algebra if it's non-trivial. So here's, we had a local version. So you can do a local version of this. So you look at HAC, which would be all those H2 functions that the restriction to A is C measurable. And then we're saying, okay, we want that we look at the orthogonal projection of H2 0 onto H2 0A, and we call it an analytic pair if we get that this is, in fact, this conditional expectation restricted to A. And so the only way you can do this is essentially the same way as Alexandrov's theorem, with A to be a set in T minus 1 of B, where you have the same inner function. So the question is, what about multidimensional? And I could talk about analytic sigma algebra of the torus, and then I could look at the characters. So the characters would now be indexed by, would be a form chi n1 tensor chi n2, and I would want to look at the span where the n1 and n2 are positive. And the question is, what are the analytic sigma algebras? Okay. So, yeah. Okay, so now we're going to get to the probability theory and maybe some dynamics. So the idea is to look at the transfer operators of inner functions. You can see that the inner functions are kind of very bad, but the transfer operators, so these are at least continuous, yeah? I mean, if I want to look at them as operating on higher order distributions, then they would even be smooth. Yeah? So the idea is to try to get the transfer operator to act quasi-compactly on as a pair of Banach spaces, or a nice Banach space. This goes back to Dublin-Forte in 1937, and they had what's called an adapted pair. So you have two spaces. L is a small space contained in C. The norm of the C norm is less than the L norm, so that should be, yeah, right, okay. Let's correct that. Should be like that. And I want to know that CL closed bounded sets are C compact. Okay? So for example, you could look at Lipschitz and L1, and then by Alzella-Ascoli, so the norm is going to be, so Lipschitz functions are absolutely continuous, and with bounded Radon-Nikodym derivatives, so you take as a Lipschitz norm, L1 norm plus L infinity norm of the derivative. Alzella-Ascoli tells me that this is an adapted pair. Then there's the Soto-York in 73. So 37, 73, nice reverse there. L1 and bounded variation. Helly's theorem tells me that bounded sequence in BV has a subsequence which converges weakly to some limit. Weakly means that you converge on all points of all except for the countable points of discontinuity, which implies convergence in L1. So there we go. So we're looking at spaces of analytic functions. So the idea is that you look at, so you have something, you're having how to look at this. I mean, it's sort of like saying that you're looking at a harmonic function on a disk, which can be extended to a harmonic function of some larger disk, of radius b. So what does that mean? You're taking a function in L2, but in fact the Fourier series, I mean, if I take beta to the mod n times Fourier coefficients, that should also be finite. Okay? So these are kind of real analytic functions. Dublin-Forte operator, so it's a bounded linear operator from C into C, also from L into L, so that you have these two inequalities. The first one is that it should be power bounded on C. The second one is that there's some power, say kappa equals 1 if you want, so that the L norm of p to the kappa x is less than r L norm of x, where little r is less than 1, plus some constant by the C norm, times the C norm of x. So in other words, you can kind of eat up large L norms of images in the C space. You're only left over with a little bit there. So that's a Dublin-Forte operator. So equivalent condition is the spectral gap property. So this was Dublin-Forte for Lipschitz, I think L1, and Ionesco-Tulcea-Marinesco in general. So P should be a Dublin-Forte operator on the adapted pair. Then it's quasi-compact. In other words, there's an n, there's a theta, so that PF should be, right. Guess what? P to the n f minus a to the n f. Should be like that. So A is going to be a compact operator. It means that it's the sum, so I take finitely many finite dimensional projections and finitely many rotations around it. So that's the compact operator. If I had that P was a transfer operator for a weakly mixing non-singular transformation, then A would just be, A of F, the compact operator, would just be the integral times an invariant density. Okay, there's something called the eigenvalue rigidity property. Why is it a good thing? So Dublin-Forte wanted to use this method, this theorem, to find invariant densities. That was the idea. Turns out that it's much better for doing probability theory, but one of the things they had, you want a smooth invariant measure, so there's this eigenvalue rigidity property. So if I have an eigenvalue, then the eigenfunction is smooth. It's in L. So eigenfunction in C, then in fact the eigenfunction is in L. Okay. So here's an example. So we said that smooth inner function restrictions are interval maps. Here's a nice kind of interval map introduced by Adler. So you have interval 0, 1, Lebesgue measure T, and some partition, countable partition into intervals, so that T goes from A onto I, should be a C2 diffeomorphism for every A. The derivative is always bounded away from 0, and there's some power where it's bounded uniformly away to 1, from 1. And also I have this distortion condition. This is, you could call this a kind of Renyi distortion condition. So Adler's idea in this paper was to find justifications for Renyi's paper on interval maps, F expansions. So best example, Gauss map. And then you have that T squared is uniformly expanding. So our result actually goes back to Dublin Forte for at least the Gauss map, but you can look at the paper I wrote with Denker in around 2000. So it's a Dublin Forte operator on L1 Lipschitz. So here's a result. What's the relevance to inner functions? If I have inner function with, so I don't want phi 0 equals 0, I want Donjois point with min, Donjois-Wolff point inside the disk, finitely many zeros, finitely many singularities, then it's an Adler map. So you can kind of just, it's a calculation basically. Okay, spectral gaps. So now in general, suppose you have something which is inner, not Möbius, and phi 0 equals 0, with a restriction tau. So first result, if b is bigger than 1, and phi prime 0 is less than rho, then there's some m, so that tau to the nu minus the expectation of u, the integral, is less than m times rho to the n. So this is quasi-compactness in Kb. So that's the definition of Kb that we had with the Fourier series before. Okay, so this is telling you actually that the, what do they call it, essential spectral radius of the transfer operator can be anything which is bigger than the absolute value of the first derivative. The derivative is 0. Fixed point. Second point, so suppose that the derivative is equal to 0. So suppose phi of z equals z to the k times some other inner function which doesn't preserve 0. So has a 0 of order k, kappa. Then you have super exponential convergence, like that. And the third one is that in fact this calculation, I mean this essential spectral radius is precise. So if tau satisfies this football on some L which contains enough Poisson densities, so Poisson densities for small z, then you get that the spectral radius is going to be bigger than the absolute value of the first derivative of 0. So this is a kind of consequence of the smoothness of the transfer operator. So I should point out that there are different methods. There's a paper by Oleg Ivry and Mariusz Urbanski around the same time as ours, where they get spectral gaps, but for the transfer operators, but on different spaces, different methods. So one thing you can do with this directly from these guys, you can get central limit theorem. So there's this Gordon theory of cohomology to a martingale difference sequence. So first thing is there's a result of Leonov that exists an asymptotic variance. So if I look at I have some probability preserving transformation so that T hat is a Dublin Forte operator on L1 script L. And then you take some psi which is centered but in script L. Then I look at the expectations of psi n squared, so variances of psi n divided by n, and this converges to some limit, some non-negative limit. Equality, so it's equal to 0 if and only if psi is a coboundary. Okay? So this was taken a little bit further by Gordon a few years later, that suppose you had that sigma squared is positive, then there will be a g and a psi in L2, so that big psi is g minus gt times little psi, and psi t to the n is a martingale difference sequence. So that means that you look up ct to the n and you take the conditional expectation with all previous values, ctk up to tk minus 1, then this is equal to 0. The central limit theorem is known for things like that. So you get Billingsley's central limit theorem tells you that if I normalize Cn by the asymptotic variance times root n, then I get a standard normal distribution. And you can get that for using the cohomology. It's an L2 cohomology. So you get this for the sequence, for the Cn's. Okay, so this was basically the method used in these papers. There's 2 papers that I know about. There's Ivry-Urbanski and Nikolaus Gilbert. Okay, so we want to do something slightly different. We want to get what's called preimage or conditional central limit theorem. So you're using this Nagaev method. So suppose on one leg, here's the basic idea. You have a weakly mixing probability preserving transformation. T hat is doubling forte operator on the adapted pair. And then, in fact, everything's analytic. I mean, I can look at this in context of the surrounding operators on bounded linear operators on L. So there's some epsilon, some k, and some theta, and analytic functions on the Banach algebra. Lambda is an eigenvalue. N will be projections. And P are going to be operators, so that P to the NH minus lambda P to the N times NP times H is less than or equal to K times theta to the N norm H norm, L norm of H. So these are going to be projections, one-dimensional projections, yeah, because we started off with a weakly mixing transfer operator. So for given a C in L, with, which is centered and some T, you can define what's called a characteristic function operator, transfer operator of F, but times e to the it C. So if I iterate this n times, then I get transfer operator to the n, e to the it c sub n. So the integer of this is going to be the transfer operator of the sum of the random variables. But you can see that in fact there's an eigenvalue here, so I've got a chance of getting that the eigenvalue is going to be like the characteristic function of the marginal random variable, and the characteristic function of the sum will be like the characteristic function of the marginal guy to the power n, just the same as if I had independent random variables. So that's the idea of this Nagaev technique. Okay, expansion of the eigenvalue. The first application of this that I saw to dynamics was Rousseau-Egel, who was a student of Guy Varche in the 80s. So I have a weakly mixing probability preserving transformation, etc. And now I'm looking at PT. So what was PT? Yeah, PT was defined in this kind of way. And we want to look at the Taylor expansion. So he calculated the Taylor expansion. So if sigma squared, I think, is positive, then you get something which looks very much like something in the domain of attraction of Gaussian. So you get that if sigma squared is positive, then CT satisfies the conditional central limit theorem. So T hat n of exponential ITC n divided by n is this guy to the power n, yeah. T. One. And that's equal to the eigenvalue of this guy by Nagaev, and by the by what we've got here, this goes to the right thing, the characteristic function of the limit random variable. Okay, so here's the conditional central limit theorem for inner functions. How are we doing? So I'm running early, you should be stopping me. Or it just seems too long, huh? So phi should be non-Möbius with fixing 0. So I take a bounded measurable function, C bounded measurable. I'm going to define these perturbation operators like that. And PT was the original guy, should just be pi IT. So these are, so we're defining complexifications of the PTs that we had before. Okay, so you show direct calculation again using harmonic analysis with what you know about inner functions. So if C is some guy in KB with B bigger than 1, KB is that blank space that we had with real analytic functions. And for every little b less than big B, you get that Z goes to pi of Z is an analytic function into, it's an analytic function inside the bounded linear operators on KB. And in fact, you see that the nth derivative, you know exactly what it is, so it's exactly that. Okay, so if you're not a Lebesgue product or anything, then you satisfy this conditional central limit theorem. So we've set everything up. All we need now, according to Rousseau, is that the asymptotic variance is non-zero. So suppose that the asymptotic variance was equal to 0. By Leonov, then you'd have something in L1 or L2, so that C is equal to HT minus H. And we're going to show this can't be. So you fix something, you know, this guy is in KB, fix little b less. PT is a Dublin Forte operator on L1 KB for small t. There exists some positive t which is true. So what I know is that it's true for t equals 0. I would like to be able to prove that this is true for every t, which is real. I don't know how to prove that. But by continuity, PT will be a Dublin Forte operator for small t. So there exists one. So now you let G equal to e to the ITH, G to the G times ITC is equal to G tau. So that implies now applying transfer operator, you're going to be, you get that PT is equal, PTG equals G. So so this is an eigenfunction. So by eigenvalue rigidity, G is in KB. And you get this functional equation. Okay, if you observe this functional equation, this is smooth. This side, the left-hand side, is real analytic. The right-hand side has singularities. But you only know this for x in the radial limit set. So you know it almost surely, so no contradiction yet. Fix a point in the singularity set. By Zeidel's theorem, so now this is a more detailed version, fancier version, there are preimages of x in the radial limit set, so that preimages of x would Wn tends to V. So for every point, there are preimages of anything which goes to this essential singularity. That's Zeidel. You can check this out for the Gauss map, by the way. The Gauss map, if I look at it on the circle, it has one singularity, 0. And so there are sequences of preimages going to 0 of any point. Therefore, g of x is equal to g tau wn, which is this guy. I think there's no lambda there. Yeah, forget the lambda. Lambda equals 1. The wn's tend to v, but that's all smooth, so I'm getting that the limit there is gv e to the it cv. So g is constant. G is constant, so now look at this equation again. G is constant, so e to the it c is constant. But Psi is real analytic, so it doesn't have any jumps, so Psi is also constant. So therefore you've got that C, the asymptotic variance was positive, and by Rousseau-Hegel you have the conditional central limit theorem. So question, like I said before, I don't know how to prove that it's a Dublin Forte operator for every T. So this would give you a conditional local limit theorem and other things. And one of the other things is this question. So you can define a skew product. So it's a non-invertible skew product. Usual kind of thing, this should be pointwise dual ergodic, which I won't tell you what it is, but that would follow from the local limit theorem. But the question is this transformation ergodic? In particular, it would be ergodic. So that's why I prefer the conditional central limit theorem to the regular one for these kind of things, for dynamics. Okay, so we're up for a bit of multi-dimensional situation. So here's a copy of the first slide. So you talk about a bounded function on the bi-disk. That's a bi-disk. You call it biharmonic. Biharmonic almost surely. Yeah. Forget the almost surely. Sorry. For a bounded biharmonic function. So biharmonic function means it's a function of z and w. You fix w, and then it's harmonic in z, and you fix z, it's harmonic in w. Okay? So you've got radial limits. As you go off to the boundary. So f c s c t tends to f st, almost surely. And similar to the one-dimensional situation, this is Poisson integral. Biharmonic function is a Poisson integral of its boundary limit. So the Poisson kernels are just tensor products of the Poisson kernels on the disk. So given Psi, which is bianalytic, so bianalytic means same thing, analytic in Z for fixed W, analytic in W for fixed Z. You define the composition operator in the same kind of way. So it's non-singular just as we were before. Inner function would be a bianalytic function on the bi-disk, which has boundary limits which are on the square of the boundary. So in other words, you have a restriction on the torus instead of on the circle. So there it is. So I kind of took the liberty of defining vectors, vector characters like that. So for an inner function, same way as we had before, the composition operator is in fact composition with the boundary restriction. So you get that an inner function, for an inner function of the bi-disk, it's a non-singular map of the torus. So a lot of them are going to be, kind of rational, or, you can see that they're absolutely continuous, but they don't have to be. Okay, so that's the bit that generalizes. So let's say that the inner function on the bi-disk satisfies Boole's formula if the transfer operator, we can always define a transfer operator, of P ZW goes to P Psi of ZW. So for example, if I had just looked at Cartesian products of inner functions on the one-dimensional disk, this would be good, yeah? So if C satisfies Boole's formula, and let's take the simplest possible situation, C to the n ZW tends to 0 for every Z in the disk, then the guy is exact, same kind of thing. The Poisson kernels, they generate L1. So now is an example. So this is z squared w, zw. So c to the n zw, you can check this. This goes to 0 for every zw in D. But the restriction is also known as the cat map. This is invertible, so it cannot be exact. Invertible transformations cannot have trivial tails, they have full tails. Just like the cat. Cat even has 9 tails. You know? So, C doesn't satisfy Boole's formula. So there's a question as to, on the one hand you have product functions which satisfy Boole's formula, maybe that's it. Or maybe you have some more, but you don't have everything. Okay, so that's it. Thank you for listening. But I didn't finish yet. I have to say happy birthday to the birthday boys. There we go. Count the candles. Wow.
Questions? Remarks?
Should have stopped me before, right?
With a live audience, questions?
I might have a very small question. So you're trying to generalize this result by opinion functions to biases. Is there some reason why this is done for the two-dimensional instead of like n-dimensional?
No.
Do you think it's so you don't think it's going to be?
No, the first slide with a non-singular, there's as many as you want. Polybies. The second one, I think you can do, I think you can do, wherever you can do hyperbolic automorphisms of the tool. In fact, I don't even need just automorphisms of the tools with positive coefficients. You know? So that will give me examples. Oh yeah, there's another thing, sorry. So there's another way to do this. I mean, you could try doing this kind of thing on 3 space. Then you have upper half space, a nice hyperbolic space. You can, instead of looking at some kind of analytic maps, you can look at conformal maps. But then there's this result of Liouville, which tells you that as soon as you have a conformal map on a higher dimensional Euclidean space, then it's the restriction of a Möbius transformation. So there's nothing non-invertible. It's just, it's hyperbolic geometry and that's it. Fuchsian groups, Kleinian groups.
Any other questions, folks? No? Questions?